Hello there guys, welcome back to another epic inexorable maths video. In this video we're looking at finding the Maclaurin series for the natural log of 1 plus x. Now you might say, why, hold on, why is there a 1 in there? It's just because the natural log of x does not have a Maclaurin series. And the reason for that is because one of the criteria for a function to have a Maclaurin series is you need to be able to evaluate it and all of its derivatives at 0. But the natural log of 0 is not defined. Neither are any of its derivatives at 0. So we just use the natural log of 1 plus x. However, you'll see in a second, it's pretty nice. So I know it looks a bit random, but it's pretty nice. It's pretty useful. And you can do some really cool things with it, which I will show you at the end of this video. Okay, so now you might say, well, okay, right, well, Maclaurin series, I know how to do that. I just get my f of x. So f of x is the natural log of 1 plus x. And I'm going to differentiate it and blah, 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 blah. You can do that, yes. You can just differentiate it and evaluate it at 0 and keep doing that. Fun days, it's amazing. I'm going to show you guys, though, a different method for doing this, which I think is faster and more cool. And also, this will be really helpful in the next couple of videos. So what I'm going to do, first of all, we will differentiate the natural log of 1 plus x. So the derivative of the natural log of 1 plus x is 1 over 1 plus x, isn't it? Just because of the chain rule. You can verify that for yourself if you'd like. Now, instead of doing it again and again and again and again, I'm actually going to just rewrite the original f of x. So we're just going to bear this in mind, the derivative. I'm going to rewrite the original f of x as the integral of its derivative, and you'll see why. So I'm going to write it as the integral. So this is f of x, not the derivative, but it's the integral of the derivative. So 1 over 1 plus x dx, right? Now you might say, okay, but what about the plus c though? Because it's not going to be the same. This will integrate to ln 1 plus x plus c. So in order to get around that problem, we need to find the value of x that makes this equal to 0. Well, if x was 0, then the natural log of 1 plus 0, that's just 0. The natural log of 1 is 0. So I'm going to actually put some limits in here. I know this is very different to how normally you would do one of these questions, but trust me, it will pay off. And I'm going to do something a bit cheeky here. I'm going to put an x in the limit. And then because this is a little bit forbidden, you know, you've got an x in the limit of the integral and also as the variable, I'm just going to change the variable into a different letter. Maybe we'll do a u. It doesn't matter. And now this is totally legit again. So notice how this will integrate to the natural log of 1 plus u. And then when we evaluate the limits, it becomes the natural log of 1 plus x minus the natural log of 1 plus 0, which that term is 0. So this is the natural log of 1 plus x. Hope that that's okay. Now, why did I just do that? What's going on? That's not how you find a Maclaurin series. What's going on? It's okay. Watch this. The reason we've done this is because 1 over 1 plus u has its own Maclaurin series that's easier to get. You may also know this as the binomial series or the binomial expansion. So if I rewrite 1 over 1 plus u, so let's just forget about the integral for a second. Let's just come down here. 1 over 1 plus u. Let's get the series for that. 1 over 1 plus u. Well, this is just 1 plus u to the minus 1, isn't it? And there is a formula for this, but this series is going to be 1 plus, and then you times the power by this term here. So minus 1 times u. Next term is going to be plus the power again, so minus 1, times 1 less than the power, so minus 2, divided by 2 factorial, multiplied by u squared. And this pattern continues. So the next term is going to be minus 1 times minus 2 times minus 3, so 1 less again, divided by 3 factorial u cubed. And it keeps going, so it goes on forever. This is called the binomial series. Now, if you're not familiar with this, it's okay because actually there's a loop part. I mean, this will simplify. This becomes 1 minus u. This becomes, basically this whole thing becomes a 1, doesn't it? So plus u squared. Oh, this whole thing here becomes a minus 1. So minus u cubed. It would keep going. You'd end up with a plus u to the 4, minus u to the 5, etc. Now that looks like a geometric series, because it is. Because 1 over 1 plus u is the same as 1 over 1 minus u. And that is the formula for a convergent geometric series. This is a over 1 minus r, or u1 over 1 minus r, if you like to use u1. So a is the first term is 1, the common ratio is minus u, and it goes on forever. And this is only valid for u being between -1 and 1, otherwise it won't converge. But this hopefully should verify that this sequence here, or this sum or series, is equal to 1 over 1 plus u. So I've kind of done that in two different ways. You may be happy with just this, you may be happy with just this, or both of them. But basically 1 over 1 plus u is equal to 1 minus u plus u squared minus u cubed, etc, 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 etc. Okay, now why have we done that? Well, because 1 over 1 plus u is equal to this, if we agree on that. Well, we want the integral of this. So now our f of x, again, which is the natural log of 1 plus x, is the integral of this sequence, or this series. Writing this out again. And that goes on forever, and we're going to integrate it with respect to u, and we're going to bound it between 0 and x. So this is still the natural log of 1 plus x, if you can believe it. And then, I mean, does it get easier to integrate 1, u squared, u cubed? It's a polynomial. So, our f of x, we're just going to integrate term by term the whole thing. So 1 integrates to u integrates to u squared over 2. U squared integrates to u cubed over 3. U to the 3 integrates to u to the 4 over 4. And of course it's alternating as well between plus and minus, u to the 5 over 5. And it would just keep going, right? It just keeps going. And that's infinite. And again, the limits are from 0 to x. Now here's the thing, if we evaluate this whole thing at 0, it's still just 0 because there's a u in all of them. If we evaluate it at x, it's literally the same thing, but all the u's are x's. Which means that f of x, which is what we're trying to find the Maclaurin series of, is just this, but replace all the u's with x's. So in other words, it's just x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4 plus x to the 5 over 5 minus x to the 6 over 6 plus dot 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 on forever. This is the Maclaurin series of the natural log of 1 plus x. So as I say, as I've said it before, oh, just thrown the pen, don't need any more though, because it's the end of the video. But as I've already said, this is not the typical way to find your Maclaurin series. Typically you would differentiate it and evaluate it at 0 and plug it into the Maclaurin series formula, right? But what we've shown here is that there's actually a completely different way to do this. Some functions, when you differentiate them, differentiate to essentially functions that have a different Maclaurin series that you can just find and integrate. We will see this in the future when we do arctan and arcsine. It becomes even more useful for that. Because you may say, well, hold on, I don't know if this was really that much faster. In my opinion, it is faster. But you might say, I don't think it was. Trust me, you try and do this with arcsine, and without this method, you will not have a good day, to be honest with you. So this becomes increasingly useful for more difficult to differentiate functions. This is not too bad to differentiate. It's really not that bad. But differentiating arcsine and arctan, nightmares. So this is much faster. So this is showing you the Maclaurin series for the natural log of 1 plus x, but it's also prepping you for some of the harder ones. And this is how we're going to do some of the harder ones. And yeah, I hope that's helpful, and I hope it makes you think about finding Maclaurin series in different ways.